Hello everyone, and welcome to the next video in this series on the fundamentals of math. This is a PSS video on the on the problem solving process, and I am actually pretty excited about making this video because for the first time now I can show you one, or at least give you a glimpse of one of the power tools that you can use in algebra, and this tool will eventually transform the way you see algebra and math, and it's going to replace, believe it or not, BEDMAS. And what I'll do is in this video, as I said, I'll give you a glimpse of it. We will hone and improve and add on to this tool as we go through the videos. But today in this video I will give you sort of like an introduction to it. So just to give you an idea as to what's coming up, we will be talking about the problem solving process, and there are two main topics here. One is a sort of like a brief discussion on the structure of a word problem, just to bring awareness as to what this structure is, and the fact that there is variation in this structure. There is always ways of referencing to the quantities whose values are sought by the word problem, and the kinds of units that are expected to be used in the solution to those problems. The second component is where the fun begins. We'll talk about the two problem-solving techniques. One of them is called the step-by-step technique, and the other one is called the algebraic technique. Alright, so with that in mind, we'll start with our talk. Now, during the talk, I will be using this sample word problem as an example of how you go about thinking about problems and solving them. And let's just quickly read it once. The sample word problem says that since noon, Paula had 2 cups of tea at 24 calories per cup, 3 slices of pizza at 181 calories per slice, and a slice of cake containing 235 calories. She was inactive for 1.5 hours, burning on average 80 calories per hour. Later, she went running and burnt 340 calories. And the problem now says, calculate Paula's net intake of energy since noon. Alright, so to begin, there are generally, one would expect that there would be 2 sections in a word problem. The first one provides information on the values of certain quantities, and the second part asks you to calculate the values of one or more other quantities whose values are unknown. So if you take a look at the sample word problem here, this is the first part, where a lot of information is given to us in terms of the values of certain quantities. It tells me about the number of cups of tea that Paula had, the energy content per cup of tea. It gives me the number of slices of pizza that Paula had, the energy content per slice of pizza, the energy content of the cake, the duration that she was inactive, the rate at which she burned energy during the time when she was inactive, and then the total amount of energy that she burned when she went running. So you can see this is number of how many. This comes from counting its amount. This is the rate at which the rate of energy, the amount of energy per cup of tea. And so you can see that these are all quantities, values of quantities that are given to us. Now the second part is the sentence at the end, where it says calculate Paula's net intake of energy since noon. And here is where they ask us to find the value of a certain quantity, in this case energy, and in particular Paula's net intake of energy since noon. Now there are variations in structure, and this corresponds to the different ways that we talk, of course, and the variations are such that the request to calculate the values of certain quantities may be made using an imperative statement like calculate Paula's net intake of energy since noon, but it could also be interrogative. So it could be something like here we have it. Calculate Paula's net intake of energy since noon in calories. Or it could be posed as, what is Paula's net intake of energy since noon in calories? Now sometimes they even beg you for it, like please find Paula's net intake of energy since noon, but yeah. So there are variations in structure. Now also that when the word problem asks you to find the values of certain quantities, in some way the word problem refers to these quantities, and there is variation here as well. The reference may be explicit, like in this sample word problem on the side. It says calculate Paula's net intake of energy since noon. So we are very, very clear about what it is that we want you to find. It could, however, be the case that that this reference is made in a manner that's implicit. So here we have you started with 25.8 milliliters of a salt solution, and you have 12.8 milliliters of the solution left. How much salt solution did you use? Now you see here we're talking about how much. We're not being as clear as we could be, which would be the case if the problem said what volume of the salt solution did you use. However, it's expected that because the problem talks about volume, given the choice of the unit, milliliters, that the final answer should be computed, that they are asking for the volume of the salt solution that you used, not its mass or some other quantity that relates to the salt solution. Right, here we have another word problem. It says on average we can extract 4 calories per gram of carbohydrate, 9 calories per gram of fat, and 4 calories per gram of protein. A cup of yogurt contains 12.5 grams of carbohydrate, 6.8 grams of fat, and 11.1 grams of protein. What is the cup of yogurt's calorie content? Now you notice that in this problem, the question does not name the quantity, but the associated unit. So it doesn't say what is the cup of yogurt's energy content. It says what is the cup of yogurt's calorie content. In such cases, the reason that you hear people use the unit is because they want you to know that not only do they expect that you will find the value of the quantity energy that's associated with the unit calorie, but that value should be computed using the calorie as the unit, not joule or some other unit of energy. However, although it would be preferable if the quantity was named, so one could say, what is the cup of yogurt's energy content in calories? But this is a shorter way of talk. It's very common in everyday life for people to talk about calorie gain and calorie loss when they should say energy gain and energy loss. Nothing wrong with that, so long as you are aware of the fact that the quantity behind this unit calorie is actually energy. Now in my talk, for some time I will be formal and be very clear about what it is. I will name the quantity to be very clear about what it is that we want to find. However, in everyday life, like everybody else, for example, I don't go around saying what is the cup of yogurt's energy content. I would say what is the cup of yogurt's calorie content as well. Okay, so just as quantities, a word problem usually expects that the value that you compute, the value of the quantity when you compute it, uses certain units. And what units should be used? The word problem may refer to them in an explicit manner or an implicit manner, or it may be the case that convention sets the standard as to what unit should be used. A few examples on this. Calculate the mass of a molecule of H2O in AMU. The atomic mass of H is 1.008 AMU per atom, and then atom of O has a mass of 16 AMU. Now, first of all, if you're not familiar with chemistry, the notation H2O says that there are 2 hydrogen atoms and 1 oxygen atom in the molecule. And of course, as most people know, this is a molecule of water. Matter is made up of tiny particles called atoms, and atoms can combine in different ways they can stick together in different ways to create what we call molecules. Examples of atoms, these smallest particles of matter that retain the chemical properties, their chemical properties are hydrogen. Capital H is used to refer to this particular atom, and oxygen, capital O, is the chemical symbol for oxygen. So H2O means there are 2 hydrogen atoms, and this should be O1, but if it's a 1, we don't write the 1. It's implied. So there is 1 oxygen atom in a molecule of H2O. Now AMU is a unit of mass, like gram or kilogram or pound, except that AMU is an extremely tiny unit of mass, and as such it's a very useful kind of a unit to use when we measure the masses of such tiny particles like protons, neutrons, atoms, molecules, and so on. For now, I will not get into details of how AMU relates to gram, how small it is, but just to note that it's an extremely small unit of mass. And the unit name is atomic mass unit. Please note, it's not atomic mass. It's atomic mass unit. In fact, later on, we will see that atomic mass is a quantity. Atomic mass unit is the unit that you can use to measure that value. Right, so the atomic mass of hydrogen, H, is 1.008 AMU per atom. So one H atom has a mass of 1.008 AMU. And an atom of O has a mass of 16 AMU. Now in this problem, we are pretty explicit about what unit should be used in the computation of the mass of the molecule. It should be AMU, atomic mass unit. So this is an example of a case when the unit is explicitly named. Here's another word problem. You are traveling at a speed of 120 kilometers per hour. What distance will you cover in 2.5 hours? Now in this problem, there is no indication as to what unit should be used in the calculation of distance. It just says what distance will you cover in 2.5 hours. So it leaves the impression that I can use whatever unit of distance that I wanted, such as meter, kilometer, feet, inches. However, that's not really the case. The fact of the matter that the other values, the values that are given to us, use certain units, such as in 120 kilometers per hour, the units are, of course, the unit of speed, which is kilometers per hour, breaks down into the unit of time, kilometers, and the unit of distance, kilometers, and the unit of time, hours. And also the duration of travel is given in hours. So one would expect that because kilometers is being used in the unit for speed, then the distance will also be computed in kilometers. So this is an example of a word problem that is sort of like implicit in terms of the unit that should be used in the computation of the value of distance. Next problem, a 3.28 kilogram object is moving at a speed of 0.22 meters per second. What is the object's kinetic energy? Okay, so in this case, the unit that should be used in the computation of energy, the quantity energy, is set by convention. This is a problem that is usually taken up in science courses, physics courses, kinematics, and what it does is that in the sciences, by default, we use the units that are in SI, and anyone who takes up the study of, let's say, physics knows that the SI, the official SI unit of energy, is the joule. So one would know that the problem expects that the value of the quantity energy will be computed using the joule as the unit. Okay, everyone, so we have now covered the first topic. So again, the purpose was not sort of to give you a catalog of all the possible different variations that you might see in a word problem, but that generally there are two sections. One of them provides information, provides information as the values of certain quantities, and the other part asks you to find the value of a certain quantity. We also talk about the different ways that the word problem refers to the quantities whose values are sought, and the different ways that the word problem may refer to the units that should be used in the calculation of the values of these quantities. Now, one last thing before we move on to problem solving techniques is the number of unknowns. Sometimes a word problem may ask you to find the value of a single unknown. In basic math, those are usually the kinds of problems that one reads about. However, it is possible for a word problem to ask for the values of multiple unknowns. An example of this is the problem: an order of 40 pens and 8 binders costs $135.52. An order of 35 pens and 9 binders costs $132.56. Calculate the cost of a pen and the cost of a binder. So in this case, the problem asks us to find the values of two quantities. One is the cost of a pen, and the other one is the cost of a binder. Okay, everyone, now we come to the next part in the series, and this is about two different ways, two different philosophies in terms of how you go about solving your word problem. The first one, which is the one that is commonly used in very basic math, and also even later on as people go through the school system, is the step-by-step technique. And this technique uses logic to work out the steps that need to be taken to solve a given word problem. Now, of course, if you are solving such problems, a word problem using the step-by-step technique, and if you're only doing it for yourself, then you can, of course, solve the problem on a piece of paper, scrap paper, and make a mess of it. So long as you know what you're doing and you get the final answer, all is good. But if you want to communicate your solution, then it's expected that you will provide some explanation as to what's going on. So in this video series, the convention that I will put in place, just so that we have some kind of structure, is that for each step, once we find out what steps we have to take, for each step, we begin with a brief note on its objective. Now, when I say brief note on its objective, I mean basically naming the quantity whose value you're seeking in that step. This is followed by the calculations that need to be done, so that you can compute what it is that you want to compute. And then there is a brief closing remark on that computed value. So as an example of that, for the word problem, that sample word problem, let me go back to it. Here we have it. For this sample word problem, we can use logic. We can come up with the set of steps to solve this problem. One possible set is are these ones. Is this one. Calculate Paula's intake of energy from the cups of tea. So we would do that by multiplying 2 by 24. She had 2 cups of tea at 24 calories per cup. And then as we read the problem, it says she had 3 slices of pizza at 181 calories per slice. So step 2, calculate Paula's intake of energy from the slices of pizza. We will do that by multiplying 3 and 181. There is no need to do at this point in time. We pass over 235 calories, which is the energy content of the cake. And then we have that she was inactive for 1.5 hours, burning on average 80 calories per hour. Step 3 will be to multiply 1.5 and 80 so that we can find Paula's loss of energy due to inactivity. And once we've done all of that, then we can add and subtract. We add all the intakes and subtract all the losses to find the, Paula's net intake of energy since noon. Now here's the full solution then. So step 1, calculate Paula's intake of energy from the cups of tea. So we state what it is that we want to find in the end. In fact, what we are doing is we are telling you what the 48 is all about. Sometimes I see people write, in place of calculate Paula's intake of energy from the cups of tea, they write something like multiply 24 by 2. That's not what we are seeking. In fact, I can see that that's what you're doing. 24 times 2, you don't have to write it down here. The idea is, what is 48? Why are you multiplying 24 by 2? You're trying to find something. What is it? And that's always, in math, you always find the values of quantities. Even in each step in a solution, you're trying to find the value of a certain quantity. What is that quantity? So here we have calculate Paula's intake of energy from the cups of tea. And to do that, of course, we have to multiply 24 by 2. 24 is the energy content of 1 cup, and she had 2 cups. So in total, she had 48 calories of energy. And so we write a closing statement. Paula had an intake of energy of 48 calories from the cups of tea. Now, step number 2 is similar. We find Paula's intake of energy from the slices of pizza. And here we have to multiply 181 by 3. 181 is the energy content of 1 slice, and she had 3 slices. So in total, she had 543 calories of energy from the slices of pizza. Then she was inactive for 1.5 hours, and on average she burned 80 calories per hour. So to find the total energy lost during that time, we multiply 80 by 1.5 to get 120. This is followed by a closing statement. And finally, we find Paula's net intake of energy since noon. Now to do that, we get 48 from step 1. That was the intake from the cups of tea, and 543 for the slices of pizza. The 235 is the energy content of the cake, and then she had a loss of 120 calories when she was inactive, followed by a loss of 340 calories when she went running. And in the balance, then she had an intake of 366 calories. And we have a closing statement again. Since noon, Paula had a net intake of energy of 366 calories. Again, I would like to bring your attention to the fact that every step, the opening statement in every step names the quantity that whose value should be computed. Okay, so this is the step-by-step solution to this problem. Now, one problem with this step-by-step approach is that it tends to become longer and longer and less efficient. Now, there are actually many problems with this step-by-step approach. Although, before you take up the algebraic technique, you should know something about how to solve the most basic problems in a step-by-step approach. No question about that. So in the school system, at early stages, they should, of course, continue teaching kids how to work out the basic problems by taking certain steps. But at some point, you'll find that the step-by-step solution becomes inefficient. In fact, later on in the series, I will show you, for example, with some problems on money problems or problems in chemistry, you'll find that certain problems could take 2 to 3 pages before they're done if you follow the step-by-step approach, whereas the algebraic approach can solve those same problems on 2 lines. This is a lot of improvement in terms of efficiency. You'll find that algebraic solutions are much easier to construct once you get used to the syntax of the language. You'll find that they are much more meaningful, and if anything goes wrong with them, you can fix the problem very quickly. But in addition to these already pretty impressive kinds of advantages, and others, by the way, there are some major advantages to the use of the algebraic technique. Now, to explain how the algebraic technique works, I would like to begin by letting you know that there are 3 stages in this technique. Stage number 1 is called modeling. And this is when you take a look at all of the different quantities that are involved in the word problem, and you try to relate them in the simplest possible way. You try to relate their values in the simplest possible way. It's interesting to note that at this stage, it doesn't matter at all what information is given and what is missing. What's important is what are the quantities that are involved. Again, it doesn't matter whether the values are given or not. the question is, what are the quantities that are involved? And you try to relate those quantities in the simplest possible manner. Such a model, such a relationship is often expressed using algebra as a language. So basically, at the end of this stage, you will have an equation. Then you solve it. And now there are different ways to solve equations. The tools that I will show you, that I promote in these video series, are the ones that use semantics, because these tools happen to be the most useful, the most meaningful kinds of tools that you will use. And they by the way, quite surprisingly, they also happen to be the most efficient kinds of tools that we have for solving equations. And then following that, once you've solved the equation, you arrive at a numerical value, and you make sense of that in the context of the word problem. Basically, this is a closing statement. So model the problem, come up with an equation that relates the values of the quantities involved in the simplest possible way, then solve that model, solve that equation, and make sense of the answer. Let's take a look at an example of this. So going back to the sample word problem that we had, we're going to solve the same problem now using the algebraic technique. And of course, there is always an unknown. In this case, it's Paula's net intake of energy since noon. And the value of this unknown will at some point be computed. But for now, we don't know what it is. So we're going to use the quantity symbol E to refer to Paula's net intake of energy since noon. And we also, in brackets following this, we write down the unit that will be used in the calculation of its value. So in the equation that we will have, E will represent Paula's net intake of energy since noon, and the unit that will be used in the calculation of its value will be calorie. This kind of statement is quite common, especially if you write reports. Usually at the beginning of the report there is a listing of these of the many different quantities, quantity symbols, and what they represent, what units are used in the calculation of their values at the beginning of the report. That way there is a reference. If someone is reading your report and they come across, let's say, capital E, and they don't quite remember what it represents, they can always go to that page, the page where the listing of all the quantity symbols is, and there they will find that E is Paula's net intake of energy since noon in calories. Now, and also note that your reader may know that E is energy, but not quite remember quite what energy. You may be talking about different energies in the same report, and so this E would represent Paula's net intake of energy since noon in calories. Now, I would say that of all the quantities that are given in this word problem, the simplest way to relate them is to argue that Paula's net intake of energy is equal to the sum of all of the intakes minus all of the losses. That would be probably the simplest way to argue through this problem. And you notice that when I'm thinking like this, I'm not even thinking about which intakes are given and which losses are given, whether I'm trying to find the value of net intake of energy, or maybe net intake is given and they ask me about how many cups of tea Paula had. It doesn't matter what the unknown is. What matters is that the simplest way to relate all of these unknowns is to argue that Paula's net intake of energy is equal to the sum of intakes minus the losses. So we write down E, that's Paula's net intake of energy since noon, is equal to, I would like to go in order that the numbers are presented. So we begin with 24 times 2. This will compute Paula's intake of energy from the cups of tea. She had 2 cups of tea, and each cup of tea had 24 calories. Now to this, we're going to add the intake of energy from the slices of pizza, which is 181 times 3. And then to this we add the intake of energy from the cake, which was 235 calories. And now comes the time when she was inactive for 1.5 hours, burning on average 80 calories per hour. So we're dealing with a loss here. So we're going to now subtract the loss of energy, which can be computed by multiplying 80 by 1.5. And finally, we had another loss of 340 calories that resulted from Paula running. So this is what we have now. E is equal to 24 times 2 plus 181 times 3 plus 235 minus 80 times 1.5 minus 340. Okay, now before I'm going to come back to this, there is a lot I have to say about this equation, and I will show you how you work with it. But for now, let's continue with the solution, because first I want to show you the 3 stages before I talk in detail about any one of them. So next we have E is equal to, so we work out the energy intake from the cups of tea. That comes to 48 calories. And then to this we add the energy intake from the slices of pizza. So we work out 181 times 3 to get 543. Then we add 235, which was the energy content of the cake. And now we subtract the energy loss due to during the time she was inactive, which comes to 120 calories. That comes from 80 times 1.5, 120. And then we finally subtract the loss of energy due to running. Okay, now that we've completed all these pieces, we can add them and subtract them, and that we can do in one step. And we end up with a balance of 366 calories. Closing statement: since noon, Paula had a net intake of energy of 366 calories. So this is what we call an algebraic solution. Step 1, or stage 1, which corresponds to coming up with a model, is basically done after the first 2 lines. The first line specifies what the quantity symbol represents, and the second line comes up with what we call the model, the equation itself. Now you see this equation relates the values of all of the quantities that were given in the word problem in this manner. E is here, 24, that's the value of a quantity, is here. 2, again, that's the value of a certain quantity, in this case number of cups of tea, is over here. And then we have 181. So you see, you can take a look at this equation, and for every number that I've used, you can find that number in the body of the word problem. All right, so it's important for us to keep in mind that an appropriate model is such that, first of all, I can take a look at any numerical value that's used in that equation and find that numerical value in the body of the word problem. In other words, if someone began by writing E is equal to 48 plus and then keep the rest of it exactly as it is, just start with 48, not 24 times 2, but the rest will be the same. So 48 plus 181 times 3 plus, and so on and so forth. This is not a good model, because it's actually step by step. Step 1 was done in your head. You multiplied 24 by 2 to come up with 48. And then step 2 is when you put the rest of the equation together. Such equations will not be useful to us later on. It's actually pretty interesting that even if you take one step, one more step other than just writing the equation down, if you take any steps in your head or on paper, then we don't call that the algebraic technique. That's still a step-by-step technique. Okay. One last comment. This is a comment on style. It's always a good idea to write your model down by putting the numbers down in the same order if possible. Of course, that's given in the body of the word problem. So you see that 24 and 2, these relate to the cups of tea, the energy content of the cup of tea. The problem talks about the cups of tea first, and so I write the part that relates to the cups of tea first. This is followed in the body of the word problem with information on the slices of pizza, and that's what I do in my equation. My next item would deals with the energy content of the slices of pizza, and then the cake, and so on until the end. Okay, so now now that we've talked about this, let me tell you about, let's go through some of these lines and talk about them in detail. So of course, E is the opening statement, as I said, contains the quantity symbol. And there is a brief statement as to what it represents. Please make sure that you name the quantity, so the energy that's expected, followed by the unit that's used in measuring its value. The second line is pretty interesting, and you might sort of have a gut feeling as to how I put it together, but you might still not feel quite comfortable about me doing what I did when I did 24 times 2, and then I did 181 times 3, then I jumped over here and did 80 times 1.5, and you might wonder how can you make those decisions as to what needs to be done before we do the additions and subtractions. So let's talk about that, and to understand how the statement that we have here over here, E equals 24 times 2 plus 181 times 3 and so on, to find out how that works, you should train yourselves to break it up into its logical components known as terms. And a term is you can find your terms if you use additions and subtractions outside brackets to break down an algebraic expression into its logical components, which are the terms. So here's term number 1. It's 24 times 2. I put a box around it to make it stand out. So I'm using the addition here, and then the addition over here, the subtraction over here, and the subtraction here, to break the expression down into terms. So my next term would be 181 times 3, and I'll put a box around that. Then comes the next term, which is just the number 235. We put a box around this one. And then comes 80 times 1.5. This is the fourth term on the right side of the equality sign, which is what we call the right side of the equation. So now we have 80 times 1.5, which is a term, and then comes 340. And that's one term on its own. On the left side, by the way, we also have terms. In this case, there is only one term that contains the quantity symbol E, and here is that term. So this is the proper way to look at an algebraic equation when there are only additions, subtractions, and multiplications. You always use additions and subtractions outside any brackets that might be present. Initially, you don't even look inside brackets, and we will have a lot more to say about brackets in the problems coming up. But for now, please keep in mind that you use additions and subtractions outside brackets to break your expression down into terms. This is term number 1 on the right side of the equation, term number 1, term number 2, number 3, 4, and 5. Now, what's pretty interesting about each term is that each one computes the value of a quantity. So term number 1 computes the intake of energy from the cups of tea. Term number 2 computes the intake of energy from the slices of pizza. Term number 3 computes the intake of energy from the cake. Term number 4 computes the loss of energy due to the period of time when Paula was inactive. And finally, the last term computes the amount of energy that she lost when she went running. So if you take a look at it now, this algebraic equation is really a way to encode the following sentence. It says, Paula's net intake of energy since noon. Now, how do I know that? It's right here. Paula's net intake of energy since noon is equal to, with focus on terms, intake of energy from the cups of tea plus the intake of energy from the slices of pizza plus the intake of energy from the cake minus energy loss during the time she was inactive minus energy loss when she went running. So you see, it starts to make a lot of sense now. And this is how you should start to look at algebraic equations. To go with bedmass and say, let me remove the terms for a minute. Okay, back to what we had. No boxes right now. To go with bedmass and say, you go from left to right and do your multiplications. So you would do 24 times 2, and then go from left to right and do your your next multiplication. Let me actually show you what we're looking at here. Okay, so here I have, let's type the number again. So 24 times 2. Yes, and then 181 times 3. And then we have 235. Then we subtract 80 times 1.5, and then subtract 340. Okay, so here we have the equation, and now if I go with BEDMAS, then what I would have to do, my apologies, just a second, let me just bring this up just a bit. Okay, so if I follow BEDMAS, then I have to go from left to right and do 24 times 2, and especially if I do the step-by-step BEDMAS to get 48, and then we write down plus 181 times 3, and then we put down plus 235, and then we have minus 80 times 1.5, so 80 times 1.5, and then we have minus 340. And now I go to the next line, and here I have to now go from left to right again. Yeah, BEDMAS says go from left to right and do multiplications. So now I have 48. I shouldn't add because the next thing to do is to multiply 181 by 3. That gives me 543, and then to this I add 235 and subtract 80 times 1.5, and then we subtract 340. Now we go again from left to right, and we do the next multiplication, which is 80 times 1.5. All right, so we have now 48 plus 543 plus 235 minus 120 minus 340. And now again we no more multiplications. All the multiplications are done. BEDMAS. Now the next one is additions. So we do 48 plus 543, and that gives me, let me see now, 1, 9, and 5. Hopefully all is correct. Then add 235, and then subtract 120, and then subtract 340, and then we go to the next line, and now we add 591 and 235, and that gives me a 6 and a 2 and 7, 8. Okay, and then we have minus 120 minus 340, and then we go to the next line and we get 706 minus 340, and hopefully everything is correct, all of my intermediate calculations. Some of these additions I just did in my head, and finally let's say we get the correct answer of 366 calories. So we followed BEDMAS, and what did we really do? Follow, go from left to right, do the multiplications, do the additions, do the subtractions. Yes, we got the answer. Is there much meaning in what we did? BEDMAS sounds like it's just a rule that you follow for no other reason that people told you that it works, and it does work. But there are so many problems with it. One problem is that it's not very easy to get information from why we are doing BEDMAS. There is so much concentration on what needs to be done next, M or A, or is it division or what, that attention, you cannot really focus on why you do what you do. Moreover, you take a look and see that this is a pretty long process. Because I do one operation per line, it takes forever to finish this problem. And this is a simple problem. As problems get more and more difficult with brackets coming in, and then later on, if you have, let's say, fractions in your equations, these lines can become very, very, very long. And the amount of time that you spend writing all of this down the chances and chances are always higher. The more you write, the higher the chances that something may go wrong. Like just by mistake, you may copy 1.5 as 1.4. And so there are problems with BEDMAS. And what I'm telling you is the tip of the iceberg, by the way. There are some major issues with BEDMAS. The approach that I told you about, where you take the equation that's given and you break it down into terms, makes a lot more sense. As you noticed yourselves, it was very meaningful for me to come up with the terms E and 24 times 2, then the term 181 times 3, 235, 80 times 1.5, and 340. And so let me show you the terms one more time. So we have on the right side of the equation, we have 24 times 2, so there's term number 1. And then we have 181 times 3, here is term number 2. Then we have 235. You notice that I'm using additions and subtractions outside brackets to break the expression down into terms. Next we have 80 times 1.5, so we put a box around it, and then we have 340, and we put a box around that. Okay, so those are the terms. Now, as I said before as well, every term refers to the value of a certain quantity. I would like to also put a box around E so that we know that terms are on both sides of the equation. Okay, one thing you should not do is to get into the habit of putting boxes around your terms in your equations. It's best to just see them. And the reason for it is because it will be time consuming. It will be something that you will get a habit of, you get into the habit of doing it, and then it becomes a problem. You constantly have to draw boxes before you can make sense of what's being said. A much better approach is to just make sure that when you write your numbers down, that you put a bit of space on either side of addition and a bit of space on either side of subtraction. That way your terms will stand out, and it's very clear to see them, visually see them, without having to draw boxes around them. Let me remove the boxes around the terms. And so here we have now, you see, compare what I've written here, where I put a bit of space on either side of plus, and a bit of space on either side of every subtraction sign, every minus sign. Compared to this line where I didn't use spacing. You see, this one looks like it's a jumble of numbers, but this one is much clearer. Owing to the spacing here, I can visually group 24 and 2, and then 181 times 3, and then 235, and so on. Okay, so one question comes up as to why is it that we can use additions and subtractions to break an expression into terms? Why is it that we did not use, let's say, multiplications or later on divisions or other things to break an expression into terms? And this takes me back to the major theme that I use in the series, that mathematical tools and algorithms, they sort of arise as a result of our increasingly more complex problem-solving needs. And if you think about the increasing level of complexity of the kinds of problems that we solve, the kinds of problems that require that we add or subtract are the simplest kinds. And that's why additions and subtractions are given priority in breaking an algebraic expression up. They reflect the fact that adding and subtracting are the simplest things that we do. Okay, so if I may just take a bit of time to put the terms back down. Now we are done with the stage where we model the word problem. What we did is we came up with a statement that describes what the quantity symbol that we will be using in our equation is, and then we came up with my apologies, and then we came up with an equation that models the problem, and we broke it down into terms using additions and subtractions outside brackets. Okay, so one more to put in brackets, in a box, that would be 340. All right, so this understanding that this is how an algebraic expression breaks down. Again, this is an agreement that we break an expression along the lines of additions and subtractions. Shows us that the way we view an expression would be in terms of stuff that we will be adding and subtracting. Now, these stuff may need to be worked out, of course, before we can add them and subtract them, which naturally leads us to do 24 times 2, then 181 times 3, 235 stays, 80 times 1.5 becomes 120, and then 340 goes here. So we understand that instead of now using BEDMAS, which says go from left to right, do the multiplications, don't ask why, we understand that we need to really work out these boxes before we can add and subtract them. And we do that. We work them out and we get the statement 48 plus 543 plus 235 minus 120 minus 130. All right, the last thing that I would like to, now this is important though, one of the key things that I would like to mention now is that you should train yourselves to see each addition and each subtraction to apply to what follows it. So I know that usually when we see addition, we look at two numbers on the left and right, but I would like you to also have this ability to see this addition as saying that you're going to add 543. Now what you're going to add it to is a good question, but for now please keep in mind you're just adding 543. And this addition says that at some point you're going to add 235, and this one says at some point you're going to subtract 120, and so on, and this one says you're going to subtract 340. So every addition and every subtraction applies to the term that follows it. This is good to know. This view is a good view to have, because what it does is that it tells me that when I work out an expression that has only additions and subtractions, I could go from left to right, but I could also do it in a different way. If I wanted to, for example, I could do the addition of 235 at this point, or if I wanted to, I could take this and move it to the end and do it at the end. So if you think about it, if you had an intake of 235, whether you add it right at the beginning or somewhere along the way or at the end, so long as at some point you add the 235, it doesn't matter when you add it. So that means that an expression such as 48 plus 543 plus 235 minus 120 minus 340 is identical to the expression 48 plus 543 minus 120 minus 340 and then plus 235. These two will evaluate to the same value. And all I had to do was to keep in mind that that this addition goes with 235. So if I, for some reason, if I choose to move 235 to the end, the addition goes with it. And you can notice, you can also say that the subtraction of 120, again, the subtraction is associated to 120. The subtraction can be done earlier. So I can move 120 back, but the subtraction has to go with it. So the loss of 120 should still stay the loss of 120. Right? So you can actually move your terms around like that. You could even, if you wanted to, you could even start with a loss. You could say, if I have a loss of 120, I can start with a loss of 120, and then to that I'm going to add the gain of 48, and then I'm going to add the gain of 543, and what we have next, the 235. You know what, I'm going to move that one to the end as well. I'm going to move two things, move subtraction, a loss of 120 to the beginning, and a gain of 235 to the end. So now we have minus the loss of 340, and then we have a gain of 235. Yeah. So you see, these are again they evaluate to the same value. Take a look. We have a gain of 48, gain of 48, a gain of 48. We have a gain of 543, a gain of 543, same thing here. We have a gain of 543. A gain of 235 stays a gain of 235 and stays a gain of 235. A loss of 120 stays a loss of 120, and here it's a loss of 120, and same thing with the 340. So terms can be moved around so long as the operation that sits to the left of them is taken along with them. Okay, so two main things that I would like you to remember from this video then is how an algebraic expression breaks into terms using additions and subtractions outside brackets, and then how it is that every addition and subtraction applies to the term that follows it. Okay, so we are now done with the solving stage. We do the computations, we work out the terms, and then once we have worked out the terms, we do the additions and subtractions to find the answer to the problem. And then it closes with a statement. This is stage number 3 now, interpret. We close it with a statement that tells us what the 366 calories represents. So basically answers the question in a sentence. And here we have, since noon, Paula had a net intake of energy of 366 calories. Okay, so now let me go back to our list of topics. We have covered the two problem-solving techniques, the step-by-step technique and the algebraic technique. In this series, I will be focusing on the algebraic technique, and I will only talk about the step-by-step technique just to illustrate certain points. But by and large, I will not use it. The algebraic technique now, what we'll do is, in the next two videos, we're going to take a sampling of problems and apply the algebraic technique to them to solve them, just to give you sort of like a bit of feel, if you like, for what it's like to work with algebraic equations. You know, in some ways it would be the same as if I was teaching you, let's say, Spanish. I would take you to the beautiful country of Spain, and I would immerse you in the culture and let you hear people talk, and along the way give you a few tips before I take you to class and say, okay, let's now talk Spanish. And it will be the same here too. My aim in the next two videos will be to talk about different kinds of word problems and how we go about coming up with equations for them. Talk more about terms, and we have to, by the way, break terms down into their components, which are called factors. Those are things that you multiply within terms. And keep in mind, multiplication, next most complex kind of problem that we solve. So first you break along the lines of additions and subtractions, and then multiplications. So a lot of good things to come. Thank you again for watching, and I hope you will have a great day, and I will see you in the next video. And for now, I will be gone in 3, 2, 1.